So we will start without them. All right. So as you guys may already know, so our topic for today is language of mathematics. Okay. So without a further delay, let's start. So here are the intended learning outcomes for this module. So we'll talk about sets, sequences and strings, relations, equivalence relations, matrices relations, and then functions. All right. So first, let's start with set. So what is a set? So basically, it's any well-defined and unordered collection of objects called elements or member of the set. Okay. So when we say well-defined, possible to decide if a given object belongs to the collection or not. Meaning we can decide if that object is really in that set or no. Okay. That's why it's called well-defined. And then the other one is unordered collection. So when you say unordered, there is no particular order or arrangement. Doesn't matter when it comes to set. Okay. So we have here examples. So describe a listing of the elements of the set between braces. So the sets starts with curly braces, just like this one. Okay. And then anything that is inside of that curly bracket, which is separated by a comma, those are the called elements. So as you can see right here, we have a set wherein it contains 11, 12, and then 30. Okay. So each of those number, we call those elements. So we have 3 elements in total of this example. For the second example, so as you can see right here, we have a picture wherein this one is maybe an apple. I'm not sure if this is really an apple. And then we have a banana, and then we have a grapes. Okay. So this one is also a set or set of fruits. Another one is a set of combination of a picture of fruits and a number and then a letter. So as you can see, it doesn't matter what is inside of that set. Okay. So as long as separated by a comma, each one of those are one element. So we have here a total of 5 elements, 3 elements, and then 3 elements, right? So those are examples of sets. So the next thing that you need to know about sets is the notation. So here's the symbol for the notation, wherein this one is actually a Greek letter, wherein the name of this one is epsilon. Okay, so it is used to denote an element of a set. Okay, so if we have this one to denote an element of a set, so we have the opposite of that one, which is not an element. Okay, so this one is the same symbol with an epsilon, but with a slash on it. So this one denotes that the object is not an element. Okay, so we have an example here. So 3 is an element of S. So here with this one as 3 is an element of set S. Okay, so for you to be able to appreciate what is this symbol, so we have here an example. So set of all positive integers less than 4. Okay, so meaning it is any set that is less than integers, which is less than 4. So we have here 1, 2, 3. So as you can see right here, it says here order is not important. So you can arrange this one in any order that you want. So as long as you have met the requirements, which is less than 4 or integers less than 4, so we can have 1, 2, 3, 2, 1, 3, 3, 2, 1, and so on and so forth. And we also have here B, wherein the same, wherein it is also following this restriction, wherein it's only positive integers less than 4. So we have here 1, 2, 1, 2, 3. So as you can see, all of our numbers or all of our elements inside of our set is not more than 4. Okay. And if you're going to take a look on this one, it says here A is equal to B. Why is that? So if you're going to take a look on the set A, okay, this one is like individually 1, 2, 3. But for this one, it's 1, 2, 1, 2, 3. So you may have already noticed that if there is a repeated elements inside of the set, that doesn't really matter, okay? Because in a set, if there is a repeated element, okay, or a repeated value, so you can just remove those and then retain the individual unique elements. So as you can see right here, letter A or set A is equal to set B, okay, regardless of how many repeated elements of inside of that set. All right, so next one, here is the basic properties of sets. So sets are inherently unordered. So just like what I've said a while ago, arrangement doesn't matter. Okay, so as you can see right here, we have ABC, ACB, BAC, BCA, and so on and so forth. So all of those are just equal with each other. Okay, order doesn't matter in a set. Okay, so all elements are distinct or unequal. So multiple listings make no difference. So if A is equal to B, then ABC is also equal to AC. Why is that? Because again, A and B has the same value. Wherein, since they have the same value, you can just remove this A or you can just remove this letter B. So that is why this ABC is equal with AC. Okay, wherein A has a distinct value and then C also has a distinct value. So same with this one. So they could be equal with BC, AA, BA, BC, CC. So as you can see, most of those sets contains only two elements. Okay, if ever you're going to simplify. Okay, so we can simplify a set by eliminating the repeated elements inside of it, and then just retain one distinct element. Right? So did you guys get this one up to this point? Is everything clear?
Yes, sir.
Yes, sir.
All right. So if you have a question or clarification, yes. All right. So if you have a question or clarification, so feel free to ask me anytime or as soon as possible. Okay. I don't mind getting interrupted while having our discussion. So it's okay to me. Okay. All right. So the next one here are the examples of set. So we have number one, the set of V. Okay. So here's the variable for the set V of all vowels in the English alphabet. So it can be written as, so anyone who wants to answer number one, so you can use our chat box to answer number one. So we have a set called V, where inside of that set is in a vowels in the English alphabet. Anyone who wants to volunteer? So I'll count 5 seconds. If none, then I'll just be the one who's going to answer it. So 5, 4, 3, right? E. So I'm not really sure if this one is I or L. Okay. But anyway, so the answer of Mr. Ryan. So you guys cannot see this one because this one is a direct message, but this one came from Ryan Roger. I don't know what his last name, but Ryan Roger. So yeah, V is equal to A, E, I, O, U. Okay. So here's his answer. A, E, I, O. Okay. So these are the English vowels. Okay. How about number two? Who wants to answer number two? The set O of add positive integers less than 10. So it can be expressed by positive integers less than 10. Anyone? So, right, so coming from Miss Chelsea, so it's 13579. Okay, but then again, since this one is a set, so you have to complete your answer. So it should be, oh yeah, something like that. So just like the answer of Mr. Ulmano. So a set O, wherein it contains element of 13579. Right, so that's the correct answer for number two. How about number three? Set C, a positive integer is less than 100. So it can be denoted by, anyone? Who's trying to answer number three? Is there someone? So that my waiting time is worth it. Because if none, right, so coming from Miss Ian Cariel, and Mr. Kirk, and then Mr. Reister. So all of you got the correct answer, okay? So instead of listing every element, so you can actually have, a triple that, meaning it's incrementing by one from, so where do you get that incrementing by one? So from your first three elements, so 1, 2, 3, okay? And then counting up to 99, all right? So the three of you got it correctly, okay? So very good. So that's how you uh, make a set out of a statement, right? Okay, so we have another example here. So we have letter A, wherein it's contained 1, 2, 3. So elements can be written as 2 is an element of A or 4 is not an element of A. So as you can see right here, this is our sample set, wherein this one contains or can be denoted as 2 is an element of A. Okay, because it is true that 2 is really an element of A because it's inside of that set. But for 4, okay, as you can see right here, this one is a symbol wherein it is not an element because we cannot find this 4 inside of set A. Okay, simple as that. And another thing that you need to take note here is number 1 or 1 and a set wherein it contains 1 are different. Okay, they are not the same with each other because 1 is just a number, and then this one, a curly bracket, close and open, wherein it has a number 1, is actually a set. Okay, so anything that has a curly bracket, close and open, something like this, is already a set. Okay, wherein this set contains number 1. Okay, and similarly, this one is different from this one. Okay, so this one is a set wherein it contains 1, but this one is a set wherein it contains again another set. All right, so if you're going to analyze this one, for 1, okay, or for set wherein it contains 1, 1 is an element of this set, but set 1 is not an element of set 1. Okay, because if it's an element, then it should be just an element because this one is already a set. Okay, so it cannot be an element if it's already a set. So the next one here is a set wherein it contains another set. So this is the element of this set, okay, and then the entire set of that given set. But 1 is not an element of this double set because the element of this one is this set. Okay, so they are not the same. Okay, so we cannot simplify this one wherein just eliminate the other bracket and then just have number 1. Okay, so you cannot do that one in a set. So set 1, 2 has 2 elements, but this one, a set wherein it contains another set, has only 1 element. Okay, so we don't actually care what is inside of the next set. Okay, what we only care is the first set. Okay, and then after that, we should now take a look of the comma. Okay, if it's still inside of another set, so no matter how many elements inside of that another set, so that's still considered as one set only, or one element rather, sorry. Okay, so that is why in here 1 and 2 is just one element. Okay, all right, so once you're done with those differentiation ones at the same with set with 1, so let's talk about set builder notation. Okay, so what is set builder notation? So for any proposition or p of x over any universe of this course, so we read this one as x such that proposition x is the set of all x such that p of x. Okay, meaning in every x, it should follow this proposition. Okay, or this can be derived by specifying a property that the elements of the set have in common. Okay, like for example, this x is an element of positive integer. So this is the proposition, wherein this proposition is positive integer, and then another condition here saying that x should be less than 4. Okay, so this x should be abiding or should be following this proposition. Okay, wherein in here, what are the elements inside of this set? Can you guys tell? Positive integer, but x should be less than 4. Anyone? So yeah, it's 1, 2, and 3. Okay. Or if you want to have a complete answer, it should be something like this. Okay. How about number 2? X is a letter in the word byte. Okay. So in here, we have the word byte. So in here, maybe you could just say B, Y, D, E. Because what we're trying to follow here is the letter in the word byte. Okay. Which is something like this. All right. So that's how you read a set builder notation. Wherein this one is the following values, wherein it's abiding this proposition. All right, so here are the other notations that is being used for the set. So we have Z plus and Z, Q, and then R. For Z plus, as you can see, it's indicating positive, and Z here is an integer. So if you combine those two, meaning positive integers only. All right. So where will we start? So we will start at number 1. Okay, not at 0. So if it's Z plus positive integers, then we will start at 1 and then incrementing by 1 and to infinity. And then we have here n, wherein x is a positive integer or 0. Okay, so that's the difference of letter n and then z plus. So for natural numbers, we will start with 0. Okay, and then incrementing by 1 and up to infinity. And then we have here z, wherein there is no limitation anymore. So when we say z, it's an integer. So we cover the negative and then the positive integers. Of course, since we're now covering negative and positive, so we have to include now the 0. Okay. So there is another one which is not included in here. So we have z minus, wherein it is only considering negative integers. So in that annotation, you will start at -1 and incrementing by -1 and to infinity, of course. And then we have here letter Q, which is the rational number. Okay, so as you can see, we have here a rule for us to be able to say that this one is really a rational number. So for letter P, it should be an integer. Okay, and then for letter Q, it should be also an integer. But take note that your Q must not be equal to 0. Okay, because if your Q is already equal to 0, then that is not a rational number anymore. If you're going to put that one in our calculator, it will give you a math error. Okay, so the same with this one, so we can have a fraction A for the numerator and then B for the denominator, wherein B should not be equal to 0. Okay, so that's the only limitation for the rational number, right? And then the last one here is the R, which is the real number. So can you guys tell what are the real numbers? What is real number? Anyone? Hello? Can you guys hear me? So again, this is a direct message coming from Mr. Ryan, I don't know, Ryan, R-O-G, I don't know, Ryan Roger. So any number that we can think of, such as irrational numbers. So actually, any number that you can imagine. Okay, so it could be pi, imaginary number, those are real numbers. Okay, everything or any number that you guys can think of, those are real numbers. All right, so we have here empty set. All right, so basically from the word itself, empty, meaning it doesn't contain any element. Okay, so it can be represented by this set wherein it contains nothing. That's why it is called empty set. Or you can represent that one by using this one. Okay, we call this one a null set. Okay, null set. Okay, so it could be empty set or null set. So they are just the same. Okay, so we have example here for number 1. X is an element of real numbers and x squared is equal to -1. So it says here you can substitute or you can replace any x value as long as it's real number. So can you guys think a number wherein it would make this expression equal with each other? X squared is equal to -1. Anyone? Is there a number that will make this one equal?
Sir, hindi ba imaginary numbers lang?
Imaginary numbers for real numbers? Is that what you're asking?
Hindi, sir. What I mean is it's not possible kasi imaginary numbers are not real numbers.
Imaginary numbers are not real numbers. Really? Isn't it that imaginary numbers are under irrational numbers? Let's check. Real numbers. Letter I, letter I. Yeah. So there is no I in here. So yeah, maybe uh, anything aside from imaginary number are real numbers. Okay. So I thought that it was under irrational numbers, but it's not. Non-determinism will be no pattern. Yeah, I guess. So yeah, imaginary numbers are not under real numbers. Okay, so let's go back here. Anyway, so let's consider any notation that is under real numbers. Okay, aside from imaginary numbers. So is there a number that would make this expression equal with each other? Hello? Are you guys still there?
Sir, yung buong notation o yung ano lang, x squared is equal
This one
to
only.
-1?
X squared is equal to -1 only. Is there a number or is there a real number wherein if you're going to replace this x, it would make this expression equal?
No,
Negative
sir.
1. So coming from Miss Maris. No, because -1 squared is +1. So 1 is not equal to -1. Okay. So any other answer?
None, sir.
Okay. Simple as that. None, right? So that is why this one is under the example of empty set. Okay. So you can just put here empty set or null set because we cannot think any number that is or that would make this expression equal with each other. Okay. How about number 2? X is still an element of real numbers wherein x is equal to x plus 1. Is there a number that would make this one equal?
Wala po.
Okay, so none also. So again, the answer for this one is empty set or null set, right? Okay, so once you're done in fully understanding the sets, notations, and then empty sets, so you may now proceed and answer this one in our campus. So this one is only true or false, so 1 to 6, 2 points each, so a total of 12 points. Okay, so here are the elements, and then all you have to do is verify those numbers, whether they are true or false, right? So I'll be leaving this one to you now. Next one here is another secret. Oops, yeah, another secret. Why is it? Where is our first secret? First, second, two orbits. All right. Okay. So this is your first seat break, second seat break. So we have here total of 5 numbers. So listing the elements. So in here, just list the elements of the given sets. So just like the example that we have uh, had in our last slide. So number one is the set of all positive integers that are less than 10 using set builder notation. So just list all the elements using set builder notation. And then for number two, just list all the uh, elements, of course, using the set builder notation also. And then for the second one is write the set of letters in each word by listing elements of the set. So we have here 3, 4, and then 5. So again, in a set, there is they called unordered and then distinct or unique values or element. So you guys already know what to do for number 3, 4, and 5. And then in here, so since there is no indicated uh, name of that set, so just put this one inside a curly bracket. Okay, so you don't need to put a name or a variable name of that set. Okay, so that's for 3, 4, and 5. So are we clear so far? Clear or no? So any clarification? So let me know so we can discuss it now.
Answer. Clear, sir.
Answer.
All right, so it's clear.
Clear, sir.
Okay. So next we have here equal set. So from the word itself, equal, meaning letter A and B has the same element. Okay. So we have here examples where in A is 1, 2, 3, and then B here is in the form of notation, wherein x is an element of positive integers and x squared is less than 12. Okay, so if you're going to analyze this one, so if you will start with 1, so 1 squared is less than 12. So yes, which is our 1 already. And then the next one is 2. So 2 squared is still less than 12. So 2 squared is 4. So this is now the number 2. And then 3 squared is still less than 12 because 3 squared is equal to 9. So it is now the number 3. But once you substitute here number 4, so 4 squared is 16. So in that case, 16 is not less than 12 anymore. So in that case, you have to stop now. So whatever the elements that you have listed, which is okay with this rule or call this one restriction, okay, then that's the only elements that you can write. Okay, so that is why A is equal to B, or set A is equal to set B. So we also have this next example wherein the set A contains 3 elements, so basic, Pascal, and then Ada. And then letter B is Ada and basic and then Pascal. So as you can see, they have the same content, it's just a different arrangement. So again, in set, arrangement doesn't matter. So we could say here that A is equal to B, or set A is equal to B. So the same with this one. So we have here for the left expression 1, 2, 3, 4. And then for the right side expression, so x is an element of integers where x should be greater than 0 and x should be less than 5. So it's any integers, but we have another condition wherein x should be less than 0. X should be greater than 0 and then x is less than 5. So those numbers are only 1, 2, 3, and 4, right? So in that case, left side expression is now equal with right side expression. Okay. So did you guys get this one so far? Is it clear
Yes,
or
sir.
it's good then? Next, we have here subset of set. Okay. So this is a symbol for subset. So when we say subset, it is any set that is under a set also. Okay. So that is why we call it subset. Okay. So every element of A is also an element of B. So if that's the case, then A is a subset of B because all of the elements of A can be found on set B. Okay, so that is if X is an element of A and all X is an element of B, then A is a subset of B or A is containing B. So this can be written as A subset B. Okay, so the only logic here is as long as all of the elements of this set can be found on this another set, okay, that one is already a subset, right? So yeah, here are the another way or other way for you to write such a subset. So using universal, so for all X, so you guys have already know this one. This one is universal quantifier. So for all X is an element of A. Sorry, if X is an element of A, then X is also an element of B. Okay, so that is why A is a subset of B. Okay, and of course, if A is not a subset of B, then we write a subset with a slash of it. Right? So this like with our epsilon, wherein it has a slash on the middle. Okay. So here are the other examples wherein we have three sets. So set A is 1, 2, 3, 4, 5, 6, and then set B is 2, 4, 5, and then set C is 1, 2, 4, 5. So here are the possible ways to answer this such sets. So B is a subset of A. Why? Because 2, 4, 5 can be found on set A. So 2, 4, 5. Next, here is this one first. B is a subset of C. B is a subset of C. Why? Because 2, 4, 5 can be also found on set C, which is 1, 2, 4, 5. And then A is a subset of A. So as usual, whatever is the elements inside of that set can be found on itself. Okay, so that is why every set is a subset of itself. So A subset of A, B subset of B, C subset of C. Okay, did you guys get this one so far?
Yes po.
All right. So again, I'll just summarize that one in one sentence. As long as all the elements of this set can be found on this set, then this set is a subset of this set, okay, or our mother set or our superset. All right, simple as that. All right, since we now only have 1 minute, okay, so we will stop right here for now, and then we will just continue the rest on the part 2. Okay, so goodbye for now, and see you on part 2. Okay, just wait for the link. So goodbye.